All right, welcome to my calculus videos. Today we're going to be in section 5.4 of the book that we're using. For those of you who haven't watched before, it is that one, my beat up and heavily taped version. And the topic today is linearization. And what that means is that there are functions that if we look at really, really closely, they appear to be linear as long as we stay within a certain limit. So even a curve, if we zoom in enough, it's going to look like a straight line. So the question is, how do we do this and how do we utilize it? So first thing, let's just have a couple definitions. The derivative. We know that the derivative dy dx is the limit as delta x goes to 0 of change in y over change in x. But that means that if we're talking about small values of delta x, we could say that the derivative is approximately equal to the slope. What do we mean by small? Well, that's really the key. But what we can do is we can try, and then we can calculate the error. And if the error is small enough, then we can say, hey, good enough for this application, and we can keep using it. I'm going to split this into two videos, possibly three, depending on how long the videos are, because there's a lot of examples. There's not much here, but there's a lot of examples. So let's get started. We're going to start with a quick exploration of a fairly complicated looking function. If you don't have your TI or whatever graphing calculator, you might want to grab that out right now, pause the video, come back, because I'm going to ask you to look at some things in your calculator as we work our way through this video. So the function f of x equals x squared plus 0.0001 raised to the power of 1/4 plus 0.9. And the first thing I'm going to ask you is, diving into your calculator, what appears to happen at 0,1. So I'll let you pause the video. I'm also actually going to pause the video because I'm going to pull up my calculator on my computer and take a look there. So we'll be back in just a second. All right, so I'm back, you're back. And I've pasted in a copy of a standard Zoom window. I use Zoom 6. I always start with Zoom 6 anytime I'm doing a graph. And what I see there is that there appears to be either a corner or a cusp right there at that point. Now, looking at the function, I know that that's not true. So let's take a look algebraically and see why I know that's not true. So the derivative of this function, well, first I'm going to use the power rule. So I've got 1/4 times all that stuff to the negative 3/4 x squared plus 0.0001 times chain rule says the derivative of the inside, which is 2x, and I get 2x over 4 times x squared plus 0.0001 to the 3/4 power. Now, clearly, x squared plus 0.0001 never equals 0. Which means that this derivative exists everywhere, including at x equals 0, which means there can't be a corner or a cusp at x equals 0. Hopefully that makes sense to you. So what is the derivative at 0? What do we know about this line at x equals 0? Well, That's just going to be 0. 2 times 0 divided by something, we get 0, which means that as we're looking at this point right here and the graph comes in, the slope right there, the tangent to this function, whatever it does, that tangent, whoops, no, y doesn't equal 0, y is equal to 1, must have a slope of 0. All right, so let's look at this graphically. Here's what I want you to do. I want you to go to your calculator and zoom in. So we're talking about the zoom function again. Choose number 2 in. And what you're going to do is you're going to arrow your cursor up until your cursor is approximately at 0, 1. That's going to center your zoom window at that point right there. And I want you to do this, say 3 or 4 times. Come back and tell me what you see. All right, welcome back. So here's what we notice after 3 or 4 zooms, that we start to see that that is flattening out. There's an actual curve there. It doesn't look like a corner or a cusp anymore. So here's what I want you to do next. I want you to do more zooms for a total, including the 3 or 4 that you did, of 9 zooms. And I want you to see what the graph looks like when you get to 9 zooms. So go ahead and pause. Here we go. This is 9 zooms. Notice that the graph looks linear. The bit of the graph that I can see right there looks like y equals 1. There's a bit of a wiggle right at the edge of my window right there. But from negative 3.815 times 10 to the negative 5th to positive 3.815 times 10 to the negative 5th, in other words, a small change in x, my graph looks linear. All right, so what can we do with this? Well, if we know that the slope is equal to 1, if we know that the slope is equal to 0, we've written the equation of the linearization. If I stay close to x equals 0, then f of x is approximately 1 for very small values of delta x. So what does a linearization look like? Well, here's what we know. We know that we have a point a comma f of a on some function. We know that the slope of that function at a is the derivative at a, which means that we could write the equation of the tangent line as y minus f of a equals the derivative at a times x minus a. We are going to define a new equation, L of x, which is a linearization, and that's equal to f prime of a times x minus a plus f of a. So this is a linearization at or around x equals a. All right, I'm going to stop this video right now, and well, you know what? No. I'm going to stop this video right now, and I will come back in video number 2 with some examples. All right, thanks for watching.